Now we're going to look at a special case of Snell's law. Consider the following. Let's pretend we're underwater and we place an object under the water. So water is a more dense medium than air. Water has a higher index of refraction. It has a greater tendency to bend light. So let's put an object under the water, whatever, a brick or something. And coming from this object would be an infinite number of light rays going at various different directions. Some of the light rays would be going straight up and would be transmitted through the surface of the water. There will be light rays that will be going off at various different angles. A light ray coming off at this angle, incident to the surface in this manner. Part of the light ray would be refracted because it's going into a medium which has a smaller index of refraction. Then the angle of refraction will be greater than the angle of incidence, and therefore the refracted ray is refracted away from the normal line as it's going into the lighter medium. Now note, even though the light ray is being refracted, there's always a portion of the light ray that is being reflected. When a light ray is being transmitted through a surface, there's always going to be part of the light ray that will be reflected back into the medium. It is such that, of course, as we mentioned before, the angle of incidence would always be equal to the angle of reflection. The angle of refraction, which is the angle between the refracted ray and the normal line, can be calculated according to Snell's law, where n1 sine theta 1 is equal to n2 sine theta 2. So this is all a review so far of what we've seen. But let's go further out. The further out we go is the more that the angle of refraction will be increased. And so we have this effect that is starting to occur. Well, there is such a point that if you go far enough out, the angle becomes 90 degrees. In other words, if you were to draw a normal line, you would have theta here, which would be our angle of incidence as the light ray hits the surface. Well, we went out so far that this theta, which should be our angle of refraction, is 90 degrees. So there is no angle of refraction because there is no refracted ray. The ray that should have been refracted is now going into the surface of the medium. The angle such that the ray is no longer refracted and no longer reflected is called theta c, the critical angle. Now, if we were to go beyond theta c, just a little bit more beyond theta c, or much further beyond theta c, all light rays would be reflected back into the medium. That's called total internal reflection. All light rays coming from the object would be reflected if the angle of incidence is greater than the critical angle. So now let's put this in practical terms. Imagine that you had a pool, a large pool, and the pool was empty. There was no water in the pool. You put a brick at the bottom of the pool and you start walking away. Well, once you get to the other end of the pool, you look back and you see the brick. Because the brick, you put the brick right there in the pool and there's no water. That's normal. Now imagine that there is water in the pool and you put the brick at the bottom of the pool. Well, what this is telling us is that you can start walking away, and you look back and you will see the brick. But it gets to a point that you will walk so far away beyond the critical angle where light is coming from the brick, you will walk and you will look back and you cannot see the brick because all the light coming from the brick is being reflected back into the medium, reflected back in the water. It is not being transmitted any longer. So that you look back and where you were before, when there was no water, you clearly saw the brick there. But now that there is water there, and that's a more dense medium with a greater index of refraction, then you can no longer see the brick because you are beyond the critical angle. Furthermore, imagine that you have a friend that's in the water, in the pool, and you're right at the side of the pool and you're looking at your friend, and then you start walking away. As you walk away and you look back at your friend, does their body seem to be more and more elongated or more squished together as you're looking at the part of their body under the water? The body becomes more and more squished together. Sorry, there's not a better scientific word for squished. And the reason is that as you're going out, now imagine that the object O here, your friend's feet, as you're going away from them and you're looking back, you see this light ray. This light ray makes you think that the image is here, your friend's feet, which actually is a virtual image. So you think that their feet is way up here, but their feet they're really down here. But as you walk away, the feet start to rise because of the refracted ray coming from below the surface of the water. And finally, so how do we calculate the critical angle? Well, it's pretty straightforward. Let us imagine that the index of refraction of the substance below the surface, or water, is N1, and the index of refraction of the substance above, or air, is N2. Then what we get is N1 sine theta 1, which in this case is N1 sine theta C. So we have N1 sine theta C is equal to N2 sine theta 90 degrees, because it's 90-degree angle here. So we get N2 sine 90. And of course, you know that sine 90 is 0. Psych. Sine 90 is 1. And of course, you must know the sine of 0 degrees, 90 degrees, 45 degrees, 60 degrees, and the cosine of these angles as well. We will look at the triangles shortly in order to help you remember the cosines and sines of these various angles. But certainly sine 90 you should recognize as being 1. So sine 90 is 1. So we get that sine theta C is equal to N2 over N1. Clearly, the value of N2 must be less than N1, because sine theta can never be a number more than 1. N2 must be less than N1. Thus, we've completed our review of reflection, refraction, and optics. We're going to learn how a television works. And in order to do so, we're going to have to learn a few concepts to do with the MCAT. Something like electromagnetism. So, we sort of played around with this concept already. That's in the beginning of general chemistry when discussing the atom. There were 4 quantum numbers. 2 of the quantum numbers had to do with magnetism. And the reason why is because in an atom there is a charge in motion. The charge is the electron. When the electron is moving around the nucleus, it generates a certain magnetism because it's a charge in motion. That's M sub L, discussed in general chemistry, so you don't have to worry about it now. But it's just that relationship between movement of a charge and magnetism. In fact, just the mere fact that the electron spins around its own little axis, just like the Earth spins around its axis, well, the electron, as it's spinning around the nucleus, also spins around its own little axis. It can spin clockwise or counterclockwise. Well, the fact that it's spinning or moving, there's a magnetism associated with that as well. So there is a relationship between an electricity, or the movement of current or electrons, and magnetism, and that's electromagnetism. Now let's look at each part individually just for a moment, and then we'll put the story together. So in terms of looking at, for example, a charge, here we have a charge plus Q, and it is surrounded by electric field lines. The rule is that electric field lines are always drawn away from a positive charge. So we have the positive charge plus Q, and we've already discussed the fact that there is a force associated with it. If we were to put a positive charge anywhere in here, the electric field lines describe where that positive charge would go. That positive charge can be called a test charge. So we have this positive charge here, but if we added another positive charge, it would move away from it, because like charges repel, opposites attract. So a positive charge would repel and move in this direction. By how much? What's the force? We discussed that already. Force is equal to QE, where Q is the charge, E is the electric field. We also discussed the acceleration in the electric field, because F is equal to ma, and if we take F as being QE, then the acceleration can be calculated as QE over m. And finally, we discussed the work in the electric field, because work generally is described as force times distance, and the force is QE. So it's QE, and it's delta, the distance away from or towards the charge, depending on the actual sign on the other charge, if it's positive or negative. So we discussed that. And later, we'll be discussing, when we talk about work in a little bit more detail, we'll be discussing the potential that charges have to move towards or away from this charge, and something called equipotential lines. So all that's to do with a particular charge. Now, magnetism. Magnetism originates in part from certain metals that have an ability to attract other metals. And sometimes this ability is just intrinsic to the type of metal. And just like in electric fields, we have a positive and a negative charge. Well, in magnetic fields, there is a north and a south pole. So that's the difference. So instead of positive and negative, we have N and S. So north and south poles. Well, in electricity, opposites attract, like charges repel. Well, in magnetism, similarly, opposite poles attract and like poles repel. In electricity, we draw the electric field lines going away from the positive charge. In magnetism, the magnetic field lines are drawn away from the North Pole. So we have magnetic field lines that would be drawn like so. And we can draw other magnetic field lines like so. And these lines, the direction of these lines would be in this direction, going from north to south. In electricity, it's going away from positive. So in other words, from positive to negative. And in magnetism, it's north to south. So these are the magnetic field lines. The magnetic field lines represents the magnetic flux. So this is the magnetic flux. Faraday's law of induction states that a change in magnetic flux induces an electric field. but are they really going to ask you about Faraday's law of induction or about bar magnets and horseshoe magnets on the MCAT? Very unlikely. The concepts that they like to ask are the following. Number one, that a changing electric field creates a magnetic field. So a changing electric field literally induces a magnetic field. So you get a magnetic induction vector, which we'll look at in a moment. The second concept they like to ask about is that in a magnetic field, a moving charge experiences a force. So we'll look at how you can calculate the force that a moving charge will experience in a magnetic field. So those are the two concepts that they like to ask about the most. So here's our charge. Let's move it. So we have a moving charge, and we know that current is defined as the movement of positive charge. So we have in this conductor or wire, we have a current I, which is moving, and we know that there's going to be an electric field experienced. We know at any given point, for example, there's going to be an electric field around the charge, directed away from the positive charge at any given point. Well, we're going to have three things at right angles to each other. We have the current. We have the electric field lines, which is at right angles to the current. And then at right angles to even the electric field lines, we're going to have the induced magnetic field vector. That's symbolized, like this is symbolized with I, the magnetic field vector is symbolized with B. And the magnetic field vector of a conductor, a charge in motion, is around the conductor. So it is a circle which is around the conductor. Now, when you go further from the conductor, the magnetic field decreases. When you increase the current, the magnetic field increases. So now we see the direction of the current. We see the direction of the electric field lines at any given point. No surprise, because we know how electric field lines are drawn. Now, we have to determine the direction of the magnetic field vector. Is it going in this direction, or is it going in this direction? We know it's around the wire or conductor, but in what direction does it move? And for this, we need to use the famous right-hand rule. So the right-hand rule, it starts with the use of your right hand, of course. And your thumb is at right angles to the rest of your hand. The idea with the right-hand rule is that you're going to point your thumb in the direction of the current. So this is not going to work. The current is obviously moving in this direction. If I put my hand with my palm downwards, it's not going to work because my thumb is pointing in the opposite direction of the current. So clearly, to use the right-hand rule, I have to put my hand like so with my thumb pointing in the direction of the current, which is towards the right. When I do so, by the way, my palm, no matter how I do this, my palm will be pointing in the direction of the electric field. So if I go like this, the electric field is moving in that direction, but the electric field lines, I can also put it in this direction or in this direction coming out and so on. These are the electric field lines, and that's described by my palm. Now, the magnetic field is described by the movement of the tips of my fingers in the student trick called grab the wire. So that's how students generally remember how to use the right-hand rule, is that to describe the direction of the magnetic field, simply grab the wire. So here's my right hand, thumb pointed in the direction of the current, and I bring my hand to try to grab the wire. And by going so and grabbing the wire, my fingertips describe the direction of the magnetic field. And so, going here, bringing my fingers around the direction of the magnetic fields, like so. The magnetic field is in this direction. So, you can see that this is the electric field line, and it creates a right angle with the magnetic field. We know that the electric field line creates a right angle with the direction of the current. So that's what I was referring to previously. So sometimes on the MCAT, what they're really looking for is to see whether or not you can apply the right-hand rule. Now, in terms of the charge that is moving through a magnetic field and experiencing a force, well, these are the mathematical interpretations of it. So I'm going to write some simplifications of Laplace's law, and that's the force is equal to QVB. Some people remember just QVB, which is Q the charge, V the velocity of the charge, and B is the magnetic field. So that's given by the magnetic field vector. Now it's cross B. So this is called a cross product. And a cross product means that in actuality it's QVB sine alpha. And alpha is the angle between V and B. So that's a cross product. This can also be written as ILB. IL cross B. And I'm sure you knew that already, or you could have figured it out easily. Why? Because this is the velocity. Velocity is in meters per second. Here's the charge, coulombs. But we know if this is meters per second, if this is velocity, meters per second, this is coulombs, that's the charge. We know that charge over time is current. Charge over time is current. Very important equation to remember. So charge over time is current, so we have charge over time times distance. So we have current times distance. Really, it's written as IDL, but we don't do any calculus on the MCAT. But IDL, and it's cross B, which means it's a cross product again, meaning it's B sine alpha. These equations you do not need to memorize for the MCAT, but you do need to know that there are three things that are right angles to each other. You've seen that and how that works, and this is the math behind the ideas of the charge that's moving through a magnetic field experiencing a force. And for the units, we have force, of course in newtons. These are SI units. We have charge, coulombs. We have velocity, it's meters per second, so the distance in meters. And we have B, which is the magnetic field, and that's in units called Tesla. Okay, so how does this all relate to how a television works? Well, first of all, we're going to talk about the cheapest TVs on the market. We're not going to talk about plasma TVs or LCD or flat screen televisions, because that's physics, which are a little bit more advanced, just a little bit more advanced, but mostly use similar concepts in terms of how the light is created, and you're able to see images like the image you're seeing now if you happen to be watching this on a flat screen TV. But nonetheless, the cheap models are based on a cathode ray tube. And a cathode ray tube is an evacuated tube, meaning it's in a vacuum, there's no particles in it, and it has a positive terminal and a negative terminal. So here's a positive terminal and a negative terminal. And then there's an electron gun which will shoot out electrons into this evacuated area so that it doesn't hit any particles. The electrons will go through this evacuated area, and clearly, because there's a positive electrode and a negative electrode, and these are electrons negatively charged, they will be deflected upwards. And by changing the voltage or the difference in charges from on the both sides, positive and negative side, you can actually change by how much it's being deflected upwards. In parentheses, or in brackets I should say, let's do some quick MCAT questions. They love to ask about cathode rays. I don't know why, but what they like to do is instead of sending electrons through the cathode ray, tube, because that's too simple, right? If you send electrons through, you know how it's going to be deflected. What they'll say is beta particles, for example. And a beta particle is an electron, so you know that it will be deflected upwards. Or they can call it an alpha particle. And an alpha particle, as you know, is the helium nucleus, and that will be deflected downwards. Or they can say a gamma particle goes through the cathode ray tube. And if a gamma particle goes through, you know that a gamma particle, or a gamma ray, same thing, is electromagnetic radiation. And therefore, it has no charge. It's not actual mass. It has no charge, and therefore, it would go through the tube and it will not be deflected upwards or downwards. Now this is the positive electrode, negative electrode. Positive electrode, it's the anode. You may remember from general chemistry that anions are negative ions. Anions are negative ions, anions. So anions are attracted to anodes. So the positive terminal of a battery is the anode. And so this is the anode, and this is the cathode. So this is the cathode ray tube, and now let's get closer to the television set. So here we have our electron gun. Here we have our cathode. Electrons are coming out. And then we have over here our anode. So this is positively charged. Positively charged. So the electrons coming from the cathode are attracted to the anode, going at very high speed, and they can go through here after they've developed sufficient speed and so on, and they will hit a screen. Now the screen, on the inside of the screen, it has a phosphor or a fluorescent material that is all on the inside of the screen. And the idea of fluorescence is as follows. A fluorescent material is hit by a certain energy, either light energy or, in this case, electrons. So it's hit by a certain energy. The atoms get excited and the outer electron will go up to a higher level. Then the electron at one point will go back down to its native level. When the electron is going back down to the native level, it releases energy. That energy is converted into light. So the fluorescent material is chosen to produce certain light energy when it comes down to its native or resting state. And so the light that it would be emitting would be the primary colors, red, blue, green. And so by manipulating these primary colors, we can see all the colors of the spectrum. So this is the fluorescent material that is on the that's painted on the inside of the screen. Then the electrons that are coming in here, they are painting your screen as you're watching right now about 60 times per second. So it is incredibly fast as it's going through and painting the screen, giving the different colors and so on. So we have the electrons coming out. We have the screen. We have the fluorescent material that's giving the color, the dynamics, the movement, and so on that you're watching right now. But how do we control the electrons? How do we focus them on the screen? How do we make them turn left or right and give proper movement and so on? So what force will be able to control those charges? Of course, by now, hopefully you're thinking, it must be a magnetic force. And you would be right. It's a magnetic force. And so at this point here, there are electromagnets. I'm sure nobody's ever seen a schema like this of a television set, but it gives you the basic idea. So here there are electromagnets, And all that means is there are copper wires that are wound tightly. So electricity is going through the copper wires. And we know that because there's current and the current is in motion, current is charge in motion. Because we have charge in motion, that means there's magnetism associated with it. And by manipulating the amount of current that is going through the wire, we can manipulate the magnetic field. So the magnetic field is where the electrons are going through, and by manipulating the magnetic field, it manipulates where the electrons are going to go, focusing the electrons and manipulating where they go left, right, or whatever. And all that is based on the magnetic field created by electromagnets. And these electromagnets are possible because a charge in motion creates magnetism. And it's that force that can be manipulated. Well, that's electromagnetism. It's not too bad. And there is one last idea about electromagnetism that we need to peek at before we move along, and that's the electromagnetic spectrum. We will now look at the electromagnetic spectrum. Electromagnetic radiation exists in all frequencies and wavelengths. And we know that radio waves in the electromagnetic spectrum must be really low energy waves. After all, there are tons of radio waves going through your body right now, and it doesn't seem to have any negative effect. And on the other side of the spectrum, there are gamma rays, and clearly those are high energy form of radiation, because we know that gamma rays are given off in nuclear reactions. And what do we have in between? So we have radio waves, we have microwaves, infrared. This is the visible part of the electromagnetic spectrum, so that's visible light, and ultraviolet rays, which are a little bit more high energy waves, right? You can get a sunburn, you can get cancer if you're exposed to it for prolonged periods of time. X-rays, you know, same thing, having an X-ray from time to time, very safe, but you notice the technicians and the doctors, they all wear lead aprons while you're having the X-ray, so it's not the kind of thing that you want to have several times a day. And finally, gamma rays, which are given off in nuclear reactions. So this is the electromagnetic spectrum. We have, and of course you can even calculate, you know, which one's high frequency, low wavelength, and so on, because you know the equations, which you absolutely have to memorize. One is E is equal to HF, which is E is the energy, H is Planck's constant, F is the frequency, so that means high energy means high frequency. And then the other one is V, the velocity, is equal to lambda, the wavelength, times F, the frequency. So that means in a given medium, the V, the velocity, is constant. So that means increasing the frequency, high frequency, low wavelength. So, and of course the velocity in the electromagnetic spectrum, we're talking about the velocity of light, and the velocity of light in a vacuum is 3 times 10 to the 8 meters per second. So in the visible part of the electromagnetic spectrum, we have the mnemonic Roy G. Biv to remember the colors. And there's red, below red is infrared. So there's red, orange, yellow, green, blue, indigo, and violet. And above violet is ultraviolet. So this is the mnemonic for the visible colors. And of course these are the colors of a rainbow, or the colors that are refracted when light goes through a prism. These are the colors that come from that as well. So what does electromagnetism have to do with the electromagnetic spectrum? How is it related to light? Well, first we have to start that conversation with discussing the dual nature of light. Light behaves sometimes like a wave and sometimes like a particle. We've discussed already the wave behavior of light, when we talked about reflection, refraction, diffraction, etc. In terms of the particulate nature of light, this is called a photon, and it's exhibited in the photoelectric effect, which made Einstein famous. Well, I guess that and E equals mc squared and relativity, you know, that kind of stuff. But when you use your digital camera, you get to experience both. What happens is you have light that's entering your digital camera, refracted by the lens, and focused on a CCD chip. That's not on the MCAT. And when the light, so the light is acting as a wave as it's being refracted. Then when it hits the chip, it acts like a particle because it hits the atoms on the chip and it knocks electrons off the atom. So it acts, that's when it's acting like a photon, and that is similar to the photoelectric effect. And those electrons create a current, and the current can be measured and then interpreted by your camera, and then the camera is able to determine what the image must have looked like in order to have that effect on the CCD chip. So that has both characters of light are demonstrated by using your digital camera. I'm sure you thought about that every time you used it, or you will in future, hopefully. Okay, now what about this electromagnetism? What about that part? Well, we talked about light as behaving like a wave sometimes. So what happens is that in one plane there is an oscillating electric field. In another plane, which is at 90 degrees to the electric field, is an oscillating magnetic field. The electric field and the magnetic field, say for example they're going towards you, as there is light right now that's going towards your eyes. They go towards you, they move towards you in a direction where the combined waves is at 90-degree angles to each individual wave. In other words, we have the electric field oscillating up and down in this direction, like my thumb. We have the magnetic field oscillating in this direction, like this finger. And then the direction of the field is towards you as it's moving, the light is moving towards your eyes. So each field is at 90 degrees to the other. Now, the ratio of the electric field to the magnetic field in light is equal to the speed of light in a vacuum, 3 times 10 to the 8 meters per second. In other words, the electric field is way greater than the magnetic field when it comes to light. And that wraps up electromagnetism. We are now going to start problem solving. These problems will involve forces, motion, gravitation. Most importantly, we will be resolving forces into their components. These problems are very basic. They're first year college or university level, and these problems are commonly tested on the MCAT exam. Let us look at our first problem. So, at the first year college level, usually complicating factors are eliminated. So this is a pulley system, and what you would be told in the problem is that this is a frictionless pulley and these are weightless cords. So in this particular example there are 3 masses, and each of the 3 masses is 10 kilograms. The question is simple. Is this system in motion? Yes or no? I think you should consider pausing right now and consider what you would provide as an answer to this question. Is this system in motion? Yes or no? The correct answer is cannot be determined from the information provided. And here's why. Let us resolve the forces. To begin with, we have a mass here, and the mass will have its weight as a force, and that weight is downwards, and that weight we call mg. This mass will also have a force upwards, which is the string, the tension on the rope or cord or wire. So this tension upwards, which we'll call T. So the mass experiences certain forces, its weight downwards, and the tension on the string. It doesn't matter if this mass is going up or down. Either way, it will always have its weight pointed downwards, which is essentially pointed towards the center of the Earth, because that is where the gravitational force is experienced between the center of masses, of two masses, which is something that we explored earlier. And then there's the tension in the string, which is upwards. And that tension, that force, is upwards no matter if this mass is going up or down. It doesn't matter because there is a string or cord which is there, and there's going to be some force experienced by the mass. The same thing would be felt on the other side. We have downwards mg and upwards the tension. This mass would experience tension in these two directions. Clearly, the tension in the cord would be identical. In other words, the value of the tension, which is experienced by this mass, would be the same tension as in this mass, since the cord is continuous, and this is a frictionless pulley. So here is our system. Why couldn't we just say that clearly there is this is not in motion because it's perfectly balanced? Shouldn't it be not in motion? Not necessarily. All we can say is that this system is not accelerating. Big difference. And the key equation here is Newton's second law. And Newton's second law suggests that the sum of forces is equal to ma, where the sum of forces experienced by the mass is equal to mass times acceleration. Because this system is balanced, equal amount of weight on both sides, therefore there is no net force. And because there is no net force, we know that the acceleration must be 0. But does that mean that the system is not moving? Not necessarily. Because a system which is not accelerating is in a inertial frame of reference. Some people will just call it inertia. And what inertia means is that because there is no net force on the system is either at rest, not moving at all, or it is moving but with constant velocity. Thus, it is either this system is not in motion whatsoever because of its balance, or that at some point in the history of this system, someone just pushed one of these masses, and ever since that point, the system would be slowly moving, or moving at whatever velocity was the initial velocity. Because there's no friction to slow the system down, the system would be moving with that constant velocity. So the only thing that we can say about this system is that there is no acceleration. So now we can write Newton's second law. Sum of forces is equal to ma, which is equal to 0 because there's no acceleration because the system is balanced. The sum of forces experienced by this mass would be, it would experience the tension and the weight mg. The first thing we need to do is to define which direction is positive or negative. It doesn't matter which way you do it. You do it once and then you remain consistent. So we can define downwards as being positive. If we define down as positive, therefore mg, which is down, would be in the positive direction. So we would have mg, positive direction, tension T is in the negative direction, opposite to what we wrote here, minus T is equal to 0. Therefore, the tension is equal to mg. And so this is how we would resolve the forces in this problem. and most importantly are the concepts which I've described. Now let us look at a box. Here is a simple enough problem which reveals many interesting points. This is a box which is just sitting on a table. So we have this mass associated. If we were to start to resolve the forces associated with this mass, we would have, as described before, we would have the weight downwards, mg. So that is the weight of this mass. Well, that brings up some interesting points. First of all, when we have a weight downwards, there must be a counteractive force upwards, otherwise there would be a net force downwards and then this mass would accelerate downwards. So if we were to put this box on a table, the box has a force downwards, which is its weight. The table pushes up on the box with a force which we call N, the force normal. There are a couple of important points about the force normal. To begin with, it is a counteractive force. The force normal always acts perpendicular to the surface of whatever the particular object or mass is on. So if it happens to be on a table, it acts directly upwards. But if it happens to be on an incline, we'll see later that the force normal has to be perpendicular to the incline, perpendicular to whatever surface that the mass is sitting on. So here we have our weight downwards, our force normal upwards, which is our counteractive force. Now, right now you're sitting on a chair, likely, and is the force normal of the chair, which is pushing up on you, because your weight is pushing downwards towards the center of the earth, is the force normal of the chair greater, less than, or equal to your weight? Well, imagine this. If the force normal was greater than your weight, then there would be a net force upwards. Net force means acceleration, Newton's second law. And that means every time you sat down, you would accelerate up to the ceiling. Doesn't happen. If the force normal was less than your weight, then if you were to sit down, because you would have a net force downwards, greater than the force normal of the chair, then you would accelerate downwards. And of course that doesn't happen. So if you are sitting in a chair, in equilibrium, an inertial frame of reference, you're at rest, then the force normal must be exactly equal to your weight. Now let's talk about weight. Some people may ask the question, how much do you weigh? And some people will respond, I weigh 160 pounds. Pounds. Now that's a unit of weight. So we'll look at weight. Pounds. Now, pounds would be a unit of weight in what is called the British system, sometimes called the imperial system. So I'll just write B as for British system. So that's the unit of weight. Now, some people say, if you would like to be more modern about it, someone might ask your weight and you might say 70 kilograms. Now, is 70 kilograms really your weight? Not really. Kilograms is a unit of mass. And kilograms is a unit of mass in the SI system, which stands for Système International, or the International System of Units. So this is kilograms being a unit of mass. So what is the unit of weight in the SI system? It is a Newton. Newtons are the units for weight, which is a unit of force in the SI system. I suppose because the difference between mass and weight is gravity, which is 9.8 meters per second squared, or approximately 10 meters per second squared. So it's 10 times the mass would give you your weight in newtons. I suppose people don't like saying that they weigh 700 newtons. Sounds like a lot. But nonetheless, that would be much more accurate. In the British system, the weight is in pounds. So what is mass in the British system, or the imperial system? The units are slugs. Believe it or not, they can ask a question like this on the MCAT exam. And that would be just asking whether or not you recognize what the different units are for mass and weight, etc. So, and furthermore, you should know the conversion factor between pounds and slugs. After all, it's just G, which is gravity. And G in the British system or imperial system is 32.2 feet per second squared. These are clearly constants which you must memorize. 9.8 meters per second squared for gravity, or approximately 10, and 32.2 feet per second squared, approximately 32 for the British system. When do you use 32.2 or 32 or 9.8 or 10? It depends on the problem. Basically, when you're writing the MCAT exam, you look at the question, you realize that you need to use gravity in it if it's necessary, then you look at the answers. And then by examining the answers and seeing how close the answers are one to another, then you can decide whether or not you can estimate the value of G, or whether or not you have to use a precise value of G. It's the only way to know, because you would rather estimate the value of G in order to quicken your calculations. There is one other system of units that you must know, which is the CGS system of units, which stands for centimeter, grams, and seconds. So clearly, centimeter, gram, and second system, the unit of mass must be grams, and the unit of weight or force is a dyne, D-Y-N-E. And the conversion factor you should also be able to determine, because you know this is 9.8 meters per second squared, so the conversion factor to centimeters per second squared, it must be 980 centimeters per second squared. All this we learn from a box which is not even moving. Now let's move the box. Now we're going to move the box. So let us imagine we attach a string over here and we pull on the string in this direction. Well, there will be a force associated with this, and we'll say that it's T, which is the tension on the string or cord. Well, if this box is on a surface, we are now going to get a brand new force, and that is the force of friction. The force of friction is usually symbolized by a small case f. So as we are moving in this direction, there is a new force in the opposite direction. So let's talk about the force of friction. To begin with, the force of friction always acts opposite to the direction of motion, as you can clearly see here. Can we calculate the force of friction? Indeed we can. And the force of friction is given by F max is equal to mu n, where n is the force normal and mu is the coefficient of friction. So the maximal frictional force is given by mu n. Now why would it say maximal frictional force? Well, consider this. Let's say that I had a box right here, and I put the box on a table, and I started pushing the box with the force of 1 Newton, but the box didn't move. So if the box is not moving, that means that there must also be a force going in the opposite direction of my force of exactly 1 Newton. Now, that force is the frictional force. Now, if I'm pressing on the box with 1 Newton, could the frictional force be more than 1 Newton? Impossible. If it was more than 1 Newton, then the box would accelerate towards me because there'd be a net force. If I'm pressing with 1 Newton and the box is not moving, could the frictional force be less than 1 Newton? Impossible. Because if the frictional force was less than 1 Newton, then the box would accelerate in the direction of my force because there would be a net force. So here's the box again. I'm pressing now with 3 Newtons. The same box on the same table, I'm pressing with 3 Newtons. The box still doesn't move. Well, that means that the frictional force has changed. It is now 3 Newtons. It is now exactly 3 Newtons because the box is not moving and there's no net force. Well, it gets to a point that you're pushing so hard on the box that the box just starts to move. The second that box just starts to move, that means that the force you're applying must be greater than mu n. And if you apply a force which is greater than mu n, therefore you must accelerate. If you maintain the force, not only will the object move, but it must accelerate because there's a net force, because you're above the maximal frictional force. One more thing to talk about friction. There's 2 types of friction. There's the friction of something that's not moving, static friction, and the friction of something which is in motion, kinetic friction. Thus, there is a coefficient of friction for both static and kinetic friction. And the coefficient of static friction and coefficient of kinetic friction are related thus. The coefficient of static friction is greater than the coefficient of kinetic friction always. And you may have some experience with this fact. What this is saying is, for example, say that you had a couch to move. And what it is saying is that from your experience, if you had to move a couch or a refrigerator or something very heavy, it is always more difficult to get that thing moving than to keep it moving. Thus, when something is not in motion, it's static, and you have to push on it, that effort is greater than the effort to keep it moving once it's moving. Thus, the friction of, which is the coefficient of static friction, not moving, is greater than the coefficient of kinetic friction when it has already started to move. You are now looking at another classic pulley system. And the question is going to be much the same. My question to you is, given that this is a frictionless surface, frictionless pulley, weightless cord, classic first-year college stuff, is this system in motion? You may want to pause and consider your answer. Well, the correct answer is, because for this mass there will be a force to the right, but there is no force to the left, because there is no frictional force. Usually there would be a frictional force to the left, but if we're given that this is a frictionless plane, there's no force to the left. So therefore, there is a force to the right because there's a mass here. So there's the tension on the string or the rope. So we have T here, and so this is going to move to the right. This system has to move. For this mass, it experiences its tension on the string here, and it experiences mg downwards. That's small mg because it experiences its own weight downwards. One more question. Yes, the system is moving because there's no friction. My question to you is the system accelerating? You may want to pause and consider that answer. The correct answer is definitely. And it does not matter what the masses are. It doesn't matter if this is an elephant and this is a feather. Irrelevant. Whatever mass is present here means that there will be a tension on the cord to the right. Because there is no frictional force, nothing holding this mass from moving to the right, but there is a net force to the right, this mass must move. And therefore the system will be in motion as this moves downwards. So the masses will be irrelevant to the fact that the system will not only be in motion, but it must accelerate. So what would be the relevant equations? Well, first, let us define downwards as being positive, which is arbitrary. Then we will write our classic Newton's second law, which is the sum of forces is equal to ma. The sum of forces around this mass would be mg downwards minus T, the tension, is equal to ma. Thus we have resolved the forces around this mass. To resolve the forces up here, if we were to resolve the forces in this direction, which of course would be considered the y direction, then we would have sum of forces is equal to ma, large mass m, and in this direction we would get just that the tension T is equal to ma. So whatever question they were to ask you about this problem, you would be able to solve it just understanding these basic concepts. Now we're going to have to look at some basic geometry to remind you of some concepts in order to be able to do other types of problems. Here is a very short math review, just more so as a reminder of some basic concepts that you must be very comfortable with for the MCAT exam. To begin with, some of the right angle triangles. This is the classic 45, 45, 90 triangle, and the relationship of the sides, 1, 1, root 2. Of course, the Pythagorean theorem is fulfilled here, where a squared plus b squared is equal to c squared. And so this is the relationship of this triangle. And then you have the 30, 60, 90 triangle, the relationship of its sides, 1, root 3, and 2. In terms of the functions, you should of course know sine, cosine, and tangent. And also the inverse functions of these are also explained in the book, The Gold Standard. Some students like to have remembered from high school the expression sa ka toa, which stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, such that the cosine, for example, of 30 degrees being adjacent over hypotenuse, cosine of 30 degrees would be the adjacent side, which is this side, as opposed to the opposite side. The adjacent side of 30 over the hypotenuse, which would be 2. So that would be root 3 over 2. Now, in terms of the basic math for the MCAT exam, you do need to estimate values. And that means you should have memorized root 2 and root 3. Those are the minimum roots that you should have memorized. Of course, root 2 is equal to 1.4 and root 3 is equal to 1.7. Those, of course, are estimations. But nonetheless, these you should memorize. You might be on the MCAT and get something like root 19. Well, basically, if you get a value like this, you just need to estimate. And so you know that the number 19 is between 16 and 25, but closer to 16. You know the root of 16 is 4. You know the root of 25, which is 5. And therefore, the value, the result of root 19 must be somewhere between 4 and 5, but closer to 4. And then you look at the possible answers. And you see whether or not the answers are exactly what you estimated, or if the answers are very close together, very tight. And if they are tight, then you'll need to square the answers to find which answer is closest to 19. But usually they're far enough away from each other that usually, not always, but that they're far enough away from each other on the exam that you will be able to determine whether or not you have been able to hit it right with your estimation. Other things that you should be comfortable knowing is, let's say that they were to say the sine of 48 degrees. Now the sine of 48 degrees doesn't fit with the triangles 45, 45, or 36, but clearly the sine of 48 degrees must be pretty close to the sine of 45 degrees. Doesn't mean that you would be giving a perfectly accurate estimation, but that's not what the MCAT's about. You cannot use your calculator, but you must be comfortable enough to make reasonable estimations. We will now resolve a projectile motion problem. So here is a person with a ball who's launching the ball. The ball is being launched with a speed or velocity of 25 meters per second. It is launched such that it is at an angle of 60 degrees with the horizontal. The person is standing 20 meters from a wall. We can calculate innumerable things regarding this projectile which is being launched. We can calculate its highest point which it will reach. We can calculate where it will hit on the wall. We can calculate with what speed or velocity that it will hit the wall, etc. So these are all things that can be calculated using very basic equations, equations of movement or motion or kinematics. So one of the equations that you need to memorize is the following. Vf is equal to Vo plus At. That is, that the final velocity, Vf, is equal to the original velocity, Vo plus At. The other equation that must be memorized is delta x is equal to 1/2 At squared plus VOT. So delta x, which is the displacement, and it does, even though it's an x, this x is actually a capital X and does not indicate whether or not you're looking at the displacement in the y direction or the x direction. All it's saying is that it's displacement is equal to 1/2 At squared, acceleration times time squared, plus VOT, the original velocity, times time. So, if we were to launch this projectile, one of the key things in order to solve problems regarding projectiles is time. The reason is that time is the one entity that is shared by the x and y components of this velocity. You see, when something is being launched at different angles, when we have different angles involved, like in projectile motion, like in momentum, like in inclined planes, all these different situations have different angles. These are situations where, if there are different angles, you must resolve them into x and y components. Basically, you're standardizing the problem. But when you resolve this velocity into its x component, which means along this direction, and its y component in this direction, the one thing that the x and y will share, always, is time. That's why it is frequently the first thing you need to calculate in a projectile motion problem. So let us calculate the time required for this ball to hit the wall. So we want to know the time required. In order to solve this in the most easy fashion, what we do is we examine the x direction. The reason is the following. In the y direction, we have acceleration. The acceleration is, of course, due to gravity. That works in the up and down direction. So we have acceleration in the y direction. In the x direction, of course, first year physics, basic MCAT physics, we're going to neglect air resistance or friction caused by air when the ball is moving in the air. So in the x direction, there is no acceleration. Because there is no acceleration, it really simplifies things. It means that whatever velocity the ball had initially is identical to the final velocity, because it never accelerated. Because there's no acceleration, no net force, no acceleration, therefore it remains in an inertial frame. That means it's either at rest or it's moving with constant speed. And clearly, if this leaves with an initial velocity and there's no acceleration, then it will move with constant speed, and its velocity at the end will be the velocity at the beginning. That really simplifies things. Because if we know that the velocity in the x direction will be constant, velocity comes in units of meters per second, we know the distance from the person to the wall, which is 20 meters. So we know the meters. We know the meters per second. Well then, if we have meters over meters per second, the meters will cancel, and then we'll pop out with seconds. So it's very easy to calculate the time. So what would be the initial velocity in the x direction? Let's call that initial velocity VOX. Thus we determine the original velocity in the x direction with cosine 60, since cosine 60 would give us adjacent over hypotenuse. Thus we have VOX is equal to 25 cosine 60. So to determine the time, we take the 20 meters over 25 cosine 60 meters per second. Thus meters cancel, seconds come up on top. In order to calculate this quickly and efficiently, which is key to the MCAT Physical Sciences section, divide both by 5. We have 5 left here. 5, that goes 4 times. Cosine 60, you quickly look at your triangle and determine that cosine 60 is 1/2. 1/2 in the denominator is like multiplying the top by 2. So we get 8. So the time required to hit the wall is 8 over 5 seconds. Now let's see where the ball would hit the wall. To determine where the ball will hit the wall, we are looking at the displacement along the y direction. So we would use the displacement equation. So we're looking at it along the y direction. So what we get is that the displacement delta x is equal to 1/2 a, which would be the acceleration, and the only acceleration in the y direction is gravity. So if we define downwards as, say, negative, arbitrarily, then we have 1/2 negative 10, more accurately 9.8 meters per second squared, but we'll estimate that as 10. The time squared is 8 over 5 squared, plus VOT. VO is the y direction of the velocity, and because it's the y direction here, that would be the opposite, so that would be sine of 60 degrees. So 25 sine 60 times the time t, 8 over 5. So here we can calculate the displacement in the y direction. Note, it is the displacement, meaning the distance from where the ball left the hand to where the ball would hit the wall. If the question was, where did the ball hit the wall compared to the ground, you would have to add the distance between the ground and where the ball left the person's hand, because this is displacement, the difference between the initial position and the final position of the ball. Now we're going to do some work. When you think about work in the context of physics, you should just have a Pavlovian reaction and immediately think of force times distance. So work is equal to force times distance. We're going to have to be a little bit more specific. To begin with, the word distance. It's not really distance, it's displacement, meaning it depends on the initial and final position of the object. So this is a very important part of the definition of work. The other thing is force. The force, we have to be a little bit more specific, because work is where the force is in the same direction of the displacement. So sometimes the equation is written as work, W, is equal to FD cosine theta. The cosine theta takes into account that if the force is occurring at a different angle than the displacement, then you have to take the adjacent side in order to resolve the force into its component, which is in accordance with the displacement or distance. So let's look at some of the consequences of this equation. To begin with, let's say that you were in class and you saw an overhead projector. You picked up the overhead projector, you ran around campus with it, you came back to the classroom, and you placed the projector back in the classroom in the same position. How much work was done? 0. Because the initial and final position of the overhead projector was the same. And therefore, because work is force times distance, but really displacement, if the displacement is 0, the work done is 0. So say that you were to go to the Olympics and you saw some Hungarian weightlifter lifting 500 pounds over his head. While the weightlifter was holding the weight over his head, you can go up to him and say, at this moment, you're doing no work. And that is, once again, because if the person is holding something in one position and there is no displacement, there is no work done. Another situation. Imagine there is a beach ball, and the beach ball is on the water say, you're back at Cancun or something, and the beach ball's on the water, and you apply a force downwards like this, and the beach ball moves in this direction. So you're pressing down, and the beach ball moves towards the side. What's the work done? 0. Because the force is being applied in this direction, and the object is moving in that direction, the displacement is at 90 degrees to the force. Cosine 90 is 0. And finally, what about force normal? Force normal is a counteractive force. It does not move an object through a distance, and therefore force normal, being a counteractive force, means that it does no work. Force of friction always acts opposite to the direction of motion. Thus, force of friction being cosine 180 degrees, force of friction does negative work. Now we're going to look at Hooke's law and how that applies to work. Here we have a mass attached to a spring, and the spring is attached to a wall. Now we're going to look at the motion associated with this system. We call this motion periodic motion or simple harmonic motion. Nonetheless, there is work associated with this system. As we have the mass in this position, and it moves, it's displaced a distance x, we can calculate the work done by the spring. The work is given by 1/2 kx squared. Work being 1/2 k, the spring constant, x, the displacement, squared. There is also a force associated with the spring. This force is given by Fs, that's the spring force, is equal to negative kx, where k is the spring constant and x is the displacement. Let us examine why there is a negative sign here in front of the kx term. The reason is, I will show that the spring force is always opposite to the direction of displacement. Because they're always opposite, there's a negative sign built into the equation. So here's the spring. Let's say this is the spring's native position. So we just put a spring there, we put the mass there, we haven't pushed or pulled or anything. So the mass is here. Let's say we push like so onto the spring. So we're pushing in this direction, therefore we're displacing it in this direction, squishing the spring. As we push on the mass, squishing the spring, clearly the spring will be pushing in the opposite direction. So we are applying a force in this direction, and as we do so, as we displace in this direction, the spring force is pushing in the opposite direction. Therefore, the spring force is negative kx. Now notice, when you apply a force on the mass, the spring gets smaller, applies its spring force against in the opposite direction like so. When you release, this will push the mass in the other direction, displacing it in the other direction. So in other words, the spring force restores itself. As this moves back and forth, we have energy stored in the spring and it restores its force. Therefore, we call the spring force, Fs, a conservative force because the force is restored. When energy is lost, for example, friction is a force, but friction energy is lost as heat, etc. And therefore, friction would be considered a non-conservative force, as opposed to the spring force, which is a conservative force. Next, we're going to move on to a new topic. And before we begin this topic, I'd like to ask you a question. Is it possible to be moving at constant speed and be accelerating at the same time? Think about it. And indeed, the answer is definitely. You can be moving at constant speed and be accelerating at the same time. And this is shown in circular motion. The concept comes as follows. Speed is a scalar. It has a number and a unit. For example, 55 miles per hour. Velocity is a vector, which means it has a number, a unit, and a direction. 55 miles per hour, northeast. Acceleration is the change in velocity. You can have a constant speed, 55 miles per hour, but if you're changing your direction, then you're changing your velocity. And if you change your velocity, you're creating an acceleration. Now this is a circle, and as best as I can draw it. And a circle, one can imagine, is a series of infinitesimally small lines which are always changing direction. So that if you're moving in constant speed in a circle, your direction is always changing, therefore you have an acceleration. The acceleration we call the centripetal acceleration. We calculate the centripetal acceleration as v squared over r. So v squared, v the velocity squared over r the radius of the circle. The centripetal acceleration is directed towards the center of the circle. So we can draw the vector in this way, and that is the centripetal acceleration. As we talked about in Newton's second law, where there is an acceleration, there must be a force associated with it. So the force associated with the centripetal acceleration is called the centripetal force. And the centripetal force is directed towards the center of the circle in the same direction as the acceleration. However, one might wonder, do I actually feel that acceleration towards the center of a circle every time I go into a circle? Well, consider this. Let's say that you go on an elevator, and the elevator accelerates upwards. Where do you sense the tug or the pull? You sort of feel it dragging yourself downwards. So you feel the tug in the opposite direction of your acceleration. Now let's say you go into one of those bizarre rides at an amusement park or at Disney World or whatever. And one of these amusement parks, you're going into one of these rides in which it's whipping you around at high speed. As you're moving in a circle at high speed, where do you feel the tug or the pull? You feel it towards the outside of the circle. In other words, it's as if you're accelerating towards the center of the circle and you feel the tug towards the outside. Just like when you're in a car and you're turning a corner and you feel the tug or pull towards the outside of the circle. So this is the sense that you have of the acceleration towards the center of the circle. But one important difference. When you're in an elevator and you're accelerating upwards, well, you move upwards. You actually move in the direction of your acceleration. But if you're in one of these weird rides at an amusement park and you're accelerating towards the center of the circle, you don't actually move towards the center of the circle. That actually would be quite a ride if everyone started moving towards the center of the circle. So obviously that doesn't happen. So there must be some counteractive force. It's sort of an imaginary force or a pseudo force to explain the fact that you are not actually moving towards the center of the circle. That force is called the centrifugal force. And the centrifugal force is a pseudo force, and it acts opposite to the direction of the centripetal force.